Welcome to this web lecture, Set Theory, Basics and Relations. So we're going to look into what set theory is, always slightly keeping the transport context in mind. And then there's going to be two follow-up videos where we're going to go a little bit deeper into the transport side of set theory. So what is a set according to the dictionary? The Cambridge Dictionary defines a set as a group of similar things that belong together in some way, or a group of objects with stated characteristics. So a set is a collection of items, and it's an unordered collection of items. So it doesn't matter if A comes first or B comes first. So for instance, in a transport context, a set could be a set of containers, it could be a set of people waiting for a train, or it could be a set of cities. So let's look at how we denote a set. We're saying S equals to curly braces open, curly braces closed, some content. So for instance, S equals 1, 2, and 5, or apples, bananas, and pears. We could also say S colon and then some description. For instance, E is the citizens of Eindhoven. We don't want to denote all the 200-something thousand people individually. And for some sets, we might not even know it. But we still want to say, okay, everyone who satisfies this criterion, everyone who lives in Eindhoven is meant in the set E. One special set that you should keep in mind is the so-called empty set, which we denote like this. A few sets that are always going to pop up in the context of operations research, in the context of transport, are those here. So we have the set of real numbers, which is anything between minus infinity and plus infinity. So for instance, minus 1.5, minus 1, 0, and 7, and everything that is in between. Then we have the set of integers, which is minus 3, but also 0, 1, 2, etc. Then we have the set of positive integers, which is 1, 2, 3, and so forth. We have the set of positive integers, including the 0, which is 0, 1, 2, 3. And then we have the so-called natural numbers. There's a huge discussion going on if the natural numbers contain the 0 or not. But I would like you to keep in mind is that in the context of this lecture, that the natural numbers do not explicitly consider the 0. So if you want to address the natural numbers, including the 0, please add it. Just makes it a little bit clearer and avoids any sort of confusion that might arise here. But now let's look into a little bit more transporty context already. So here we have a set of nodes, which could, for instance, be cities. And all of those cities together, all of those nodes together, make up the set A. While the set B is the empty set because it doesn't contain a single node. It still contains some area in it, but it doesn't contain any red nodes, so it's the empty set. Then we have C. C is also a set. It also contains some nodes, but it doesn't contain all of the nodes, which makes C a proper subset of A. So C is a proper subset of A. D is also a subset of A. In this case, we don't specifically specify that it's a proper subset. It is a proper subset, but we're not specifying it as such. So the difference between a proper subset and a subset is that a proper subset is not the same. So there's at least one node in A that is not in C. We're not specifying that there's no node in A that is not, that there's at least one node that is in A but not in D. It is true in this case, but we don't specify it as such. So let's look at a different example. Here we have the set E, which is of course also a proper subset of A. And we also have the set F. And the first thing that we're seeing is that F is a subset of E. We're also seeing that E is no proper subset of F because there's no node in F that is not in E. Even though if we look at it visually, it looks like F is bigger, but it doesn't contain additional nodes, which means that it is not actually bigger for our purpose. And what we can also see is that E and F are actually describing the same set. So we can say E equals to F. So now let's look at some of the sets that we saw before. So we have C, we have D, and we have E. And one thing that we see is that C and D actually overlap. So we have an intersection, which we now denote by G. G is the set intersection of C and D. So C refers to all nodes that are both in C and in D. Only being in one of the two sets is not sufficient. We also see that A is the set union of C, D, and E, which means that there's no node in C, in D, or in E that is not also in A. It is possible that there's nodes that are in A, but they're not in C, but it's not possible that there's a node in A that is not in either C, in D, or in E. So it's a bidirectional thing here with the equality, obviously. So now let's look at the sets C and G, which we both saw before already. So we see that there's some nodes in C that are not in G. And this we now denote as the set difference. So C set minus G is H. So every node that is in C but not in G is now in set H. And something that we also see if we look at this example is that the set H contains exactly two nodes. So two red dots are in H, and this is what we refer to as the cardinality of the set H. So H equals to 2. So what I would like you to take away from this introduction to set theory is, first of all, what a set is, secondly, what a couple of special sets are, and lastly, those relations of sets that we looked into. Thanks.